Okay, what I've done here is I've called up, so only the electrons move, all right? And what I've done here is I've called up the your quiz, question 1 on your Blackboard quiz, all right? So it says a brass key has a net positive charge of 1.92 times 10. That should be 10 to the negative 16 coulombs. All right, so let's just work out this problem. I mean, that might be fun. So we've got 1.92 times 10 to the negative, what did it say, 16 coulombs? Yeah, to the negative 16 coulombs, and it's positive. How many electrons did the thing lose, did the fur lose so that it became positively charged? Okay, is equal to N times 1.6 times 10 to the negative 19 coulombs, which is the amount of charge of that ran away from it. Okay, all right, so you divide those out, and you should wind up with N, when you divide these two numbers, you should wind up with N is equal to 1200. And it's just a number. It's just a number. Let's see if this is true. Boom. All right, so can an object carry this much charge? Here's question 2, 2.4 times 10 to the negative 19. What do you think? Let's take a look. Boom. No, it can't carry that much charge because charge is quantized. In other words, N has to be a counting number. 1, 2, 3, 4, 5, 6. Okay? So if you have that much charge, you wind up with like watch what happens. Watch what happens. Okay? So we've got, so we do this. We've got 2.4 times 10 to the negative 19 coulombs is equal to N times 1.6 times 10 to the negative 19 coulombs. You would have thought during the frickin' breaks and stuff, I'd have gotten my calculator. Oh, it's right here. It's handy. All right, so we can do it. Now, that's the other thing I'd like to teach you here, if I could. One thing I'd like to teach you is how do you do this stuff on your calculator. Here's the way I do it so I don't get messed up. So I'm going to divide 2.4 second e to the negative 19. Notice how I use the e key, not the 10 to the x key. The 10 to the x key is evil. All right, divided by 1.6 second e to the negative 19. And now watch what I'm going to get. Well, first of all, the e to the negative 19s will cancel, so I get 2.4 divided by 1.6, which we know is 1.5. Can't have that. I've got to have like 1 or 2. Now, some of the numbers we're going to deal with are going to be huge, and so they're rounded out, you know, because we don't put all 18 digits or something like that. All the problems you're going to have, we can squeeze it in there. But this isn't, can't have that. Okay? That was the idea behind that. Let's see what else they got here. Okay, when a glass rod is rubbed with a silk cloth, a glass rod is rubbed with a silk cloth. The rod becomes positively charged. What moves? Aha! So what lost charge? The rod lost charge to the silk. Lost negative. In other words, the electron. Oh yeah, I was going to show you the John Travoltage. I forgot. Okay, I'll show you that in a minute. Boom. Negative charge. Okay, now this one's kind of tricky. An initially electrically neutral conducting sphere is placed on an insulating stand. Okay, so let's draw a picture. I'll draw a picture of what this looks like. And then I'll show you the John Travoltage here in the next thing. Okay, so an initial electrically neutral conducting sphere is placed on it. Okay, so here we got and a negatively charged rod is brought near it, but doesn't touch it. Okay, so this will be charging by induction. All right, you can charge by contact or you can charge by induction. All right, and then without moving the rod, a wire is then attached to the sphere that connects to the ground. Why do we run things to the ground? Because the ground's positively charged. So the electrons run to the ground. Okay, That's a huge thing of just knowing about your world around you, is to know that the ground is positively charged. The earth is positively charged, and so we have all these electrons moving around that give us our light and our power and stuff like that, and we run all those poles to ground so that the excess charge, negative charge, doesn't kill us. Okay? The rod and wire then removes. What is the final charge on the sphere? Is it negative, positive, or neutral? Well, let's take a look. Let's just take a look. Okay? Here's the drawing. All right, so here's what's going on. It's neutral. It's sitting here and it's neutral. All right, so I bring in this negative rod here. All right, so I bring in this negative rod. Now, what's going to happen? If it's neutral, then it's sitting here with these positive and negative charges all sitting on it. Okay, it's got all these positive and negative charges sitting there. Okay, I bring this in close. What happens? And I attach this wire to it. If I didn't attach this wire to it, here's what would happen. No wire. Here's what happens. If I bring this rod in here that's negative, and I don't touch it, and here's this thing sitting on a stand, here's what happens. It kind of looked like this. In other words, the negative charges would run over here. And it'd still have a net neutral charge, but all the negative charges would run away. This is with no wire. With a wire. Let's put the wire back on. Here's what happens. Since the Earth has this huge run to ground as positive charge, then these electrons go, whoa, run away. And they run down here and hook up with these positive charges down here. So then you take the wire and that thing off, and it's left positively charged. That's what we just did. Okay, now I'll show you the John